we're going to start our discussion with how we can use the Navier-Stokes equations by looking at a very simple case, just laminar flow between two infinite flat plates. So this is a very simple case. It's very attractive because the geometry is very simple. It's one-dimensional. We only have to worry about how the x direction velocity, u, changes in the y direction. We can do that by assuming that the flow is what we call fully developed, which means it no longer changes in the flow direction. So if the flow is moving in the x direction, it means all of the x direction gradients are 0. We're going to look at a case here where the top surface can be moving and the plates are angled with respect to the horizontal, so you could have gravity forces be involved. Now there's a very simple question to ask. Why do we have any flow at all? What is pushing the fluid to overcome the friction caused by the viscosity? So there has to be some external force acting on the fluid, and that could be pressure, it could be friction because one surface is moving, or it could be gravity. So one of those forces has to be acting on the flow. You could also have magnetic forces or electromagnetic forces for certain types of fluids. So this type of parallel plate flow is actually a good simulation for certain real flows, mostly having to do with lubrication in automobiles and other types of machinery. We have these two plates. They're separated by a distance a. They're infinite in the z direction, which means the z gradients are also 0. And then we're going to make assumption that all the fluid properties are uniform and the flow is incompressible and steady. We do have no slip boundary conditions at both the top and bottom surfaces. So we're going to start with continuity and the u velocity equation, which are the only two that we're going to be interested in for this. We start from these basic continuity and Navier-Stokes equations. So we can assume steady state, the time derivatives drop. We can also assume that we're infinite in z, so the z direction gradients are 0. And we can assume the flow is fully developed, so the x direction gradients are 0. There's an important consequence here, because if we also assume incompressible, we can show that dv dy is equal to 0. So v is the y direction velocity. And we know from the no slip condition that v has to be equal to 0 on both the top and bottom of this set of parallel plates. So if it's got to be 0 at both ends, and the change in v is 0, it means that the y direction velocity is 0 everywhere. And that means we can cancel out the last term on the left-hand side of that Navier-Stokes equation. So the result is a simple force balance. If we rearrange the terms in the equation a little bit, we have a gravity force, where g is the g cosine theta component in the x direction. We also have a pressure force, where you have a pressure difference between both sides of the flow. And then you can have the friction forces that need to be accounted for. So the solution here is actually pretty simple. We put the u terms right here over on the left-hand side of this equation, and we integrate this twice, and we apply our boundary conditions. So that's what we'll do on the next slide. So the solution, after we integrate twice, looks something like this equation right here. What we're going to do next is start applying our boundary conditions. So our first boundary condition is that u has to be 0 when y is equal to 0 at the bottom surface, the non-moving surface. So that tells us that C2 is going to be equal to 0. Because if you replace this y with a 0, this y with a 0, and this u with a 0, you get 0 equals C2. And then we're going to apply our second boundary condition, which is at the top of the plate where y equals a, u is equal to u infinity. So we have u infinity is equal to this expression here. And we can solve this for C1. And once we do that and we substitute, we end up with an equation that looks something like this. So it's important to note that there's different terms here. We have a pressure-driven term, we have a gravity-driven term, and we have a viscosity-driven term or a friction-driven term. If the pressure drop is 0, then there's no pressure-driven term. If the plate's horizontal, there's no gravity-driven term. And if the top is moving, there's no viscosity-driven term. So we can actually consider this a superposition of several different solutions. We could actually solve this problem separately for pressure-driven, gravity-driven, and friction-driven flows. And we could get the solution for a combination by adding the results, or superimposing the results.